Initially, many software systems were built using the monolithic architecture. In this model, the entire application, including the user interface, business logic, and data access layer, is contained within a single codebase and deployed as one unit. This approach is simple, easy to develop in the early stages, and well-suited for small projects. However, as the system grows, the monolithic architecture begins to reveal several limitations. Even a small change in the code requires rebuilding and redeploying the entire application. Scaling the system also means scaling the whole application rather than only the components that need it. In addition, a single failure can potentially impact the entire system, making maintenance and operations more difficult. To address these issues, the microservices architecture was introduced. Instead of building a single monolithic application, the system is divided into multiple small, independent services, each responsible for a specific business function. These microservices can be developed, deployed, and scaled independently, while communicating with each other through protocols such as REST APIs or message queues. The microservices architecture offers many advantages, including flexible scalability, improved system resilience, and the ability for teams to develop in parallel based on different business domains. However, it also introduces additional complexity in system management, particularly in areas such as service discovery, distributed configuration, load balancing, inter-service communication, and fault handling. For this reason, Spring Cloud was created as a solution to effectively support the development of microservices-based systems on the Spring platform. Spring Cloud provides a set of tools to address common challenges in distributed architectures, such as service registration and discovery, centralized configuration, API gateways, load balancing, and fault tolerance. With Spring Cloud, developing and operating microservices systems becomes simpler, more consistent, and easier to manage. Spring Cloud is an umbrella project, meaning it is a collection of independent projects designed to help developers build and operate distributed systems quickly and efficiently. Instead of manually setting up and dealing with the complexity of distributed architectures, Spring Cloud provides standardized, production-proven solutions that have been tested and validated in real-world environments. In the latest release, Spring Cloud 2025.1.0, the framework focuses on solving common challenges in microservices architectures, including distributed configuration management, service registration and discovery, load balancing, service-to-service communication, intelligent routing, circuit breakers, distributed messaging, and contract testing between services. One of the key strengths of Spring Cloud is its ability to run consistently across different environments, from a developer's local machine to traditional data centers and modern cloud and container platforms such as Cloud Foundry and Kubernetes. Spring Cloud offers an excellent out-of-the-box experience for typical use cases. It supports centralized and version configuration, service registration and discovery, API gateway and routing capabilities, service-to-service communication, client-side load balancing, circuit breakers for fault tolerance, distributed messaging, short-lived microservices such as batch jobs or tasks, and both consumer-driven and producer-driven contract testing. To get started with Spring Cloud, the easiest approach is to use Spring Initializer at start.spring.io. When creating a project, developers simply select the appropriate Spring Boot version and the desired Spring Cloud modules, and Spring Initializer will automatically add the correct Spring Cloud BOM to the Maven or Gradle configuration. An important concept when working with Spring Cloud is the compatibility between Spring Cloud and Spring Boot. Each Spring Cloud release train is designed to work with a specific version or group of Spring Boot versions. For example, Spring Cloud 2025.1.x, also known as Oakwood, is compatible with Spring Boot 4.0.x, while older release trains such as Jubilee or Kilburn have officially reached end of life and are no longer supported. Once the correct release train has been identified, developers need to add the Spring Cloud Dependencies BOM to the project. This BOM is responsible only for managing dependency versions and ensuring compatibility between Spring Cloud modules, in the same way that Spring Boot manages its own dependencies. A major advantage of Spring Cloud is its starter mechanism. In many cases, simply adding a starter dependency to the class path is enough to enable a feature automatically. For example, by adding the Spring Cloud Config Client or the Eureka Client Starter, a Spring Boot application immediately gains the ability to load configuration from a centralized configuration server or to register itself with a service registry. Spring Cloud consists of several core projects, including Spring Cloud Config for centralized configuration management, Spring Cloud Gateway as an intelligent API gateway, Spring Cloud Netflix Eureka for service discovery, Spring Cloud OpenFane for declarative service-to-service communication, Spring Cloud Stream for building event-driven systems with Kafka or RabbitMQ, Spring Cloud Contract for contract testing between services, and Spring Cloud Bus for broadcasting events across the system. In addition, Spring Cloud also provides integrations with Kubernetes, Consul, Zookeeper, and serverless platforms. In summary, Spring Cloud is not just a framework, but a complete ecosystem that enables developers to focus on business logic while abstracting away much of the complexity involved in building and operating distributed systems. This is why Spring Cloud has become a widely adopted solution for modern microservices architectures. We begin by building a new project using the microservices architecture, an approach that is widely adopted in modern software systems due to its flexibility, scalability, independent deployment, and ease of maintenance. Instead of developing the entire system as a single monolithic application, microservices architecture allows us to decompose the system into multiple independent services, each responsible for a specific business capability and communicating with others over the network. In a complete microservices system, there are at least three essential groups of services. The first group is infrastructure services. These services do not implement business logic directly, but they play a critical role in the operation of the entire system. Typical infrastructure services include service discovery, API gateway, and config server. They help services locate each other, route requests, and manage centralized configuration. The second group is business services, which contain the core business logic of the system. Each business service focuses on a single business domain such as user management, order processing, or payment handling. These services are designed to be independent so that they can be developed, deployed, and scaled separately. The third group is observability and resilience services, which support monitoring, logging, tracing, and fault tolerance mechanisms such as circuit breakers, retries, and fallbacks. This group enables us to observe system behavior and maintain stability in a distributed environment. With this overall picture in mind, we start with the first service in the infrastructure services group, which is the discovery server. The discovery server plays a central role in a microservices architecture by registering and managing the list of active services in the system. With a discovery server in place, services no longer need to know each other's IP addresses or ports in advance. Instead, they communicate using service names. This completely eliminates hard-coded IPs and ports, which are risky and difficult to maintain, especially when services scale dynamically or are deployed in cloud and containerized environments. Within the Spring Cloud ecosystem, we use Eureka Server to implement the discovery server. Eureka Server acts as a service registry that stores information about all services in the system. When a microservice starts up, it acts as a Eureka client and automatically registers its metadata, including the service name, IP address, and port with the Eureka server. During runtime, each service periodically sends heartbeat signals to indicate that it is still alive. If the Eureka server does not receive heartbeats from a service within a specified time window, that service is marked as unavailable and removed from the registry. When one service needs to call another service, it does not need to know where the target service is running. Instead, it simply refers to the target by its service name. Eureka Server then provides a list of available instances, and Spring Cloud can work together with load balancing mechanisms to select an appropriate instance. This approach ensures loose coupling between services and significantly improves scalability, resilience, and fault tolerance. To build the discovery server, we will use Spring Boot in combination with Spring Cloud Netflix Eureka Server. This is a foundational step before implementing any business services in a microservices system. In the next steps, we will create the Eureka Server project using Spring Initializer, configure the required dependencies, start the discovery server, and verify its operation through the Eureka dashboard. Next, we move on to the API gateway, another core component in the infrastructure services layer of a microservices architecture. The API gateway acts as the single entry point for all clients, such as web applications, mobile applications, or third-party systems, to access the back-end microservices. Instead of clients calling individual services directly, all requests are routed through the API gateway. The primary responsibility of the API gateway is to centralize cross-cutting concerns that are common to all services. One of its most important roles is authentication and authorization. The gateway verifies the identity of the client, validates tokens such as JWT, and ensures that only authorized requests are allowed to reach the internal services. By handling security at the gateway level, we avoid duplicating authentication logic across multiple microservices. Another key responsibility of the API gateway is rate limiting. Rate limiting protects the system from abuse, excessive traffic, or denial of service attacks by controlling how many requests a client can make within a given time window. This ensures fair usage of system resources and helps maintain overall system stability. In addition, the API gateway is responsible for logging and request tracing. Every incoming request passes through the gateway, making it an ideal place to log request and response information, generate correlation IDs, and support distributed tracing. This greatly improves observability and makes it easier to debug issues in a distributed microservices environment. From an architectural perspective, the API gateway also simplifies the client side. Clients do not need to know the internal structure of the system or the addresses of individual services. They only interact with a single endpoint exposed by the gateway, while the gateway handles request routing to the appropriate backend services. In the Spring Cloud ecosystem, we implement the API gateway using Spring Cloud Gateway. This framework is lightweight, non-blocking, and built on top of Spring Webflux, making it well-suited for high-performance request routing. To enable dynamic service discovery and routing, the API gateway also integrates with Eureka Discovery Client. With this integration, the gateway can automatically discover available services from the Eureka server and route requests based on service names instead of fixed URLs. In practice, the API gateway registers itself with the Eureka server as a client and continuously retrieves the service registry. When a request arrives, the gateway uses this registry to forward the request to an appropriate service instance. This design supports scalability, fault tolerance, and seamless service evolution. Next, we move on to building the authentication service, auth service, which is a core business supporting service responsible for system security and access control in a microservices architecture. The auth service plays a critical role in ensuring that only authenticated and authorized users can access protected resources across the system. The primary responsibility of the auth service is to handle user authentication, including login and registration. During the registration process, the service validates user information, securely stores credentials, such as encrypted passwords, and creates new user accounts. During login, it verifies user credentials and determines whether the user is allowed to access the system. Another key responsibility of the auth service is issuing authentication tokens, typically in the form of JWT JSON Web Tokens, or OAuth2 Access Tokens. After a successful login, the auth service generates a token that represents the user's identity and permissions. This token is then sent back to the client and attached to subsequent requests when accessing protected APIs through the API gateway. In addition to authentication, the auth service is responsible for authorization and access control. It defines roles, permissions, and scopes, and ensures that users can only access resources they are allowed to use. While the API gateway performs initial token validation, the auth service provides the security foundation by defining how tokens are issued, what claims they contain, and how access rules are enforced across services. From an architectural standpoint, centralizing authentication and authorization logic in a dedicated auth service helps avoid duplication and inconsistency across microservices. Other business services can remain focused on their own domain logic and simply trust the security context provided by validated tokens. In the Spring ecosystem, the auth service is implemented using Spring Boot with the following key dependencies. Spring Web is used to expose RESTful APIs for login, registration, and token-related operations. Spring Security provides the core security framework for authentication, password encoding, and authorization rules. OAuth2 Resource Server is used to validate and process JWT or OAuth2 tokens in a standardized and secure way. Finally, Eureka Discovery Client allows the auth service to register itself with the Discovery server so that it can be discovered and accessed by other services through the API gateway. When the auth service starts, it registers with Eureka and becomes part of the service registry. The API gateway and other services can then interact with it using its service name rather than a fixed address. This design ensures scalability, loose coupling, and high availability. Next, we move on to the business services, which are the core components that implement the actual business logic of the system. Unlike infrastructure services, business services are created based on the specific requirements and use cases of the application, so their number and responsibilities may vary from project to project. Thank you for watching the video.